Okay, good morning, folks. This is the beginning of week 8. Now, remember that you still have to turn in your midterm by a deadline of 12 noon tomorrow. However, this stuff that we're going to be doing in the next 5 weeks has nothing to do with the finite element portion that we covered in the first part of the course. And just a word of caution, I think I already mentioned this, but I'll make sure you understand. This stuff that you're going to be doing is not easy. It's not the kind of thing that people can put on the side and maybe 2 weeks, I don't know, 3 weeks before the end of the course decide to catch up with it. It's going to be tough. So anyway, I just wanted to give you that caution. Now, uh, up in the first part of the course, we dealt with finding stresses. Essentially, it was finding the stresses. Okay. In other words, it dealt with forces. The next 5 weeks is not going to deal with forces. It deals with kinematics of rigid bodies. Now, obviously, as soon as I say rigid, means that it doesn't change shape, and therefore there are no stresses. Okay. Uh, this is the kind of thing that you did in your machine dynamics class with, I don't know, Dr. Alterhoff, Dr. Meinecker, and part of it in dynamics also. So let me just move on to the subject and do our first problem. This is from the other book, the book on mechanism, design, and animation. So we have a block, a 1 by 1 by 1 block that is sitting here. This dimension, by the way, means nothing, okay? And it's sitting on a track, and you're asked to make this thing move at a constant acceleration, okay? Constant acceleration. The track is fixed. The block is moving along that track at a constant acceleration, so I can say A equal to 2 inches per second squared. Now, you remember from dynamics class, first dynamics class, if you integrate this, you get velocity. So if you integrate 2, you get 2t, velocity. Of course, this is going to be velocity along the direction of the motion, because there's 3 components of velocity. Velocity in direction x. Let's say that this is x, it's this. Velocity in direction y and z, and those are 0, of course. If you integrate velocity, integrate 2t, you're going to get 2 times 1/2 of t squared, so s of t equal to t squared. So position along this track is given by that formula. You give me the time, I stick it in there, I get the position from the initial point. Stick it in there, you get velocity. Of course, acceleration is constant. Now, incidentally, if I assume that this track is 20 inches long, it doesn't have to be. This can be a mile. I don't care. Okay. Even if you don't make it a mile, you can make this thing go all the way to a mile to the right. There's no problem. But let's pretend that this is 21 inches. So if you take S and put it equal to 20, you're going to get the time that it takes for the block to reach the end, which is going to be roughly 4.447 seconds. Now, this we're dealing with a interaction between the block and this track, okay? Not in terms of forces, but in terms of joints, okay? This is called a prismatic joint. Now, there are about 12 or 13 joints that we're going to be dealing with in this course. And let me bring up the content of chapter 1, which in it I have summarized some of these. So let's go ahead and first of all look at an arbitrary block in 3 space, an arbitrary object, okay? It doesn't have to be a block, okay? This is why I said the shape of this thing doesn't matter as far as dimensions and things like that. It has some shape. It can be a sphere, it can be a block, it can be a weird cone, whatever. So it is moving in the space as a rigid body, okay? Now, the position of that rigid body, for example, the position of its mass center as a function of time, is determined by 6 numbers. Those 6 numbers is this translation from the initial point, wherever it was, in the x, y, z direction, and rotation about the XYZ axis. This is why they say that a rigid body in 3D has 6 degrees of freedom. At any point, at any time, at any point in time, if I have those expressions, I can find the position of the rigid body and orientation of it. Okay, now, if you say that, oh, this rigid body is only moving on a plane like that, then you know that it cannot get off the ground. You know that it cannot rotate about Y, it cannot rotate about X, because otherwise it comes off the ground. The only 3 parameters that it has is translation along X and Y, along the plane, and rotation about Z. This is called a planar joint. If you restrict this block to move along a straight line, such as the case that we have, then the only degree of freedom, the only parameter that determines the position of the block is distance along, for example, X direction. It's called prismatic joint. If you have a block with a hole in it and it's mounted on a shaft and it can go up and down the shaft, well, it can go up and down, but it can also rotate about this axis. So this is called a cylindrical joint, and it has 2 degrees of freedom. And there are other ones. There's spherical one and the rigid one. We're going to do all of these later on. Okay? All right. So let me kill this. We're going to go to our problem. Now, in this part of the course, when we're dealing with these topics, we're dealing with an assembly, because it's an assembly of several parts. In this case, there are 2 parts. There is the track that is fixed in space, and there is the block that is moving. Okay, so you have to do these problems as assemblies. And remember, after 5 weeks, when you do a problem like this, when you upload your results, or not results, upload your I don't know, homework or final exam, whatever it is, you give us the product and any parts that go with it. There is no analysis here. Okay, we're not doing analysis. You give us the product and the 2 parts that are making it. Okay, the block and the track. All right. Now, before I move on and do this problem for you, are there any questions? Okay, there are no questions. Let's move on. So immediately we start a product file. And right away, I'm going to save it. By the way, because I'm using I'm doing these type of problems. Last time that I was doing it, I was in the digital mock-up workbench, which we're going to get there too. It's not assembly design. You know, you have to go to the assembly design because you want to create an assembly. So, and the only way to do that is start mechanical design, assembly design. You can notice that this becomes double gear that you're familiar with. Okay. Save it, file, save management, save as, desktop, new folder, and I'll call this thing July 6. July 6. We'll put it in there. And by the way, I want to remind you that we have a lecture later today at 4 o'clock, and this life goes on. Okay, so we just move on. Another problem. All right, and we're going to be discussing Revolution in that case. Okay, now we're going to insert our first part, insert a new part in there, and I'm going to call this new part track properties. First, I'm going to make the track. The name of the part is down here. It's called part number. So track. And the part instance is track. Just remember, this instance, we didn't care about it that much when we did the analysis of assemblies in finite elements. Here, it's very important. You can ignore it. We can leave it the way it is, but it's going to be tough to find out what the joints are and things like that. We say, okay. Notice that it's made. I'm going to double click on it. We go into part design, and I will draw a rectangle that's going to make the base of this thing. Where is it? Rectangle. These dimensions mean absolutely nothing. However, we have to do the problem, so I have to tell you what sizes are. Sometimes I might even say, use your own dimensions to create this mechanism. Okay, 0.5. There we are. Exit and pad it by 21 inches. Yeah, 21 inches. Okay, good. Now I'm going to put the block on the other side. It really doesn't matter. In the drawing you had on this side, I'll put it on the other side. Okay. So insert, next part. Insert a new part. Always say no and call this thing the block. Right click, properties. The name is down here. Where was it? Number, right? Block and block. Let's make it. All it is a box, just like the bottom one. Now, on purpose, I'm not going to put it in place. On purpose, I'm going to draw it somewhere out here. So on let's say on XY plane, I will sketch a rectangle 1 by 1. One by 1. Doesn't even have to be by 1 by 1. I mean, it can be any size. So just to replicate that particular drawing that I have, I put it as 1 by 1. Good. Okay. Go to the product. Click on the floppy so that all parts and the product are saved once again. Okay, good. Now, you have to assemble this thing. When you have these problems, when you create mechanisms, you always have to anchor something. So it's foolish for me to anchor the block. It can be done, but I'm going to anchor the track. This constraints toolbar is extremely important. We're going to be using this thing over and over and over in the next 5 weeks. So anchor, there's the anchor. This, we anchored the track. And if you look closely, you see that there's an anchor right there. That means that's going to stay put in space when I move things around. Okay, now I want to put this thing and put it on that. Okay, so I'm going to say coincidence between the top face of the track and rotate it. You don't have to rotate it, but I'm going to do that so that you don't get disoriented. Update. So it shifts this up by ½ inch. Right there. And then I want to put this thing on that track. So coincidence between this edge and that edge and not upset. Update. There we are. Now I want to make sure that this thing moves from the end, that end. So the best thing, the easiest way of doing this thing, you say, okay, coincidence between this edge and that edge. But as soon as it moves there, I'm going to delete this. Because there may be a situation where you create constraints because of things like this, and later on it turns into joints, and when it turns into joints, it's not going to do what you want. So I'm going to delete this. I don't think I can deactivate it. Maybe deactivate it will do. Yeah, actually deactivate is good, because if you ever move things around, I'll delete it. What the heck? Okay, good, good. Now these are not saved, so I'll click on the floppy, and it is saved. Okay. Are there any questions? All right. Now we're going to go somewhere that you've never been before, in a workbench called DMU Kinematic. Now, I can't even see what this thing looks like. And here I can see that this is double gear and a man, blah, blah, blah. But this, I can't even describe it. So for the last, I don't know, 15 years, I call this thing, you know, on Halloween, the witches wear these pointy hats. It looks like a pointy hat to me. I don't know. It looks like that. But anyway, you go down here, digital mockup, DMU kinematic. This is the one that I showed you up there. See that? This, because I customized it, it looks like that. For you, you go to digital mockup, DMU kinematic. This is the only thing that we're going to be using in this entire workbench. Only this DMU kinematic module. Notice that right there. Your pointy hat is up there. You are in the DMU kinematic module. Okay. None of these you recognize because you haven't seen it. It's all new. It's all new. Now, I just told you that this thing is going to move along the track. Nothing exciting. Okay. This is called a prismatic joint. Any joint, you can either create it manually. You see, this DMU kinematic is extremely important. The same one with the same thing with an anchor. This is not the same toolbar, but it has an anchor in it. I'm telling you, this is important. Okay. If you look at the guy next to the anchor, you see all the joints that you have in CATIA. Okay. Now these can be done manually, or it can be done magically with something that I'm going to show you now. See that? The one that I want is right here, the prismatic joint. I can do that right here. I can do that. What it's going to ask me is give me two planes and give me two edges or two lines. But I can magically use these constraints because I did it already. I said there is a constraint between the face of the block and the face of the track. And there is a constraint between the edge of the block and the edge of the track. If that is the case, if I have already created these, I can magically turn it into a prismatic joint. If you wanted to do that manually, it'll ask you for the same thing. It asks you for two planes and two edges. Okay? But I'm not going to do that. So go here, go to this DMU kinematic toolbar, and there is double gear right next to the anchor. Double gear reminds you of a assembly design, right? Assembly design constraint conversion. And there is a little thingy here that is a magic wand. That's the magic wand. It says I magically convert your assembly constraints into joints. Now, not every joint can be created with this magic wand. This is why it's important for you to know also how to do that directly. But here I'm going to click on it, magically do it, click on it. It says, oh, you want to create a new mechanism, correct? The answer is yes, new mechanism. Oh, you want to call it mechanism 1, correct? Yeah, but I can call it anyway or anything I want. For example, how about July 6 mechanism? If you want, you can just leave it like that. I just wanted to tell you this is just a name. It says, okay, I'm going to create July 1, oh, July 6 mechanism. All right, let's call it July 1, doesn't matter. Okay, do you want me to create the joints automatically? You say, yes, I want it. Auto create. And notice that this went from 1 out of 1 to 0 out of 1 unresolved pair. So close it. Now look what happened. You had a line application at the very bottom of the tree, but nothing, no pluses. Now you have a plus. Now you have a mechanism. And the name of the mechanism is July 1, mechanism 1. Should have called it July 6. You can always double click on it, make it July 6. Maybe not from here. You can do a right click, properties, etc. Now, degree of freedom is 1. We already know this is a 1 degree of freedom. I showed you that the position of the block along the track as a function of time depends only on one thing, x, 1 degree of freedom system, if that is x, for example. Okay, where is it? Right there, 1 degree of freedom. What is the joint? Created a joint. Prismatic joint, right there. Prismatic joint. Remember we fixed the track in the assembly design? It fixed the track right here for you. There is no physics in the problem, and that's pretty much it. Now, in order to make things move, this guy must be 0. I know it's a 1 degree of freedom. I know that. But this guy must be 0. If it's not 0, you get very few part marks for making a box on the track. And that's pretty much it, because you can animate it, you can do anything basically. Now, the joint, I'm going to double click on it, and I'm going to tell the software that this parameter, this joint, is length driven. In other words, when I give you the length, the value of the length, you know where the block is. Length driven. Okay, move this thing on the side. And I want it to go from 0 to 20. I want it to go from 0 to 20. Okay, so I'm going to change this thing from 0 or 20 or 21, whatever you want. It really doesn't matter. You can make it go a mile. There's no problem. It's just that you leave the track and it keeps going. Oh, it's okay, no problem. As if the track was there. 20, I don't know, 21 or 20, doesn't matter. Okay, now notice that, let me move this thing on the side. When I say okay, it says mechanism can be simulated. That's your best friend. Now it went by very quickly. Let me do the following. Let me try it again. Let me go back here to this joint, uncheck it, say okay. Mechanism can no longer be simulated. Okay, let's double click on it again. When I select this, okay, it will say, and there's an arrow here, by the way, it says it goes that way. I don't want it to go that way. I want it to go to the left. You click on it, you say okay. As soon as you say okay, mechanism can be simulated. This is your best friend. If you don't get this, you cannot make it move. Now, if you get it, doesn't mean it's right. Just like finite elements, when it ran, it doesn't mean that you did the right stuff. The clamp, you know, the restraint may have been wrong, the force may have been wrong, the symmetry may have been wrong, but at least it runs, it does something. Same thing here. Mechanism can be simulated. Okay, very good. Now, first of all, before I do anything, let me save this. And we don't have to, all we have to do is to click on the floppy, because you click on the floppy, this is all the assembly, and we are in that workbench. It will save everything for you. Okay, good. You don't have to go through file save management unless you have become very good at it, and you rather use that instead of this floppy. Okay, good. Now, let's go back to this main toolbar, DMU kinematic. Remember the anchor? Remember on the right side of it, there was the magic wand? Remember on the left side of it, there are all the joints? This is very important. Now, the first one, if you expand this thing, there's two icons here. The top one says simulation with command. In other words, you are in charge. You make that thing move. The other one is physics in charge. It says simulation with laws. You impose the laws of physics on this planet or somewhere else, and that's what's happening. But let's do simulation with commands first, right there. You click on this, this dialog box opens up. And there's a sliding bar here. Notice that the sliding bar goes from 0 to 20. Do you remember I made the joint length to be 0 to 20, joint limits to be 0 to 20? That's where 0 and 20 come from. 0 is right here. When you move the sliding bar to the right, this guy starts moving. And it goes all the way to 20 because you made it 20. The limit you made it 20. Reset. Now notice that there is an immediate radio button here. That means as you move the sliding bar, this thing moves. If it was on request, you say, okay, so I want this thing to go, but I want to move it to this location, which is say 11.6, distance 11.6, and then I want you to show it to me right there. It goes to 11.6 and stops there. Okay? Don't want it, no problem. Reset. So this is just making things move. Very similar to, I'm sure, at some point in your grade school or high school, you wrote these or drew these things on top of the pages. It's character on top of the page, and then on the next page you made it a little bit different, and next page a little bit different, etc. So you flip the pages quickly as if the guy was animating. Basically, it's this kind of a thing. It's a cartoon. Fine. Now, You might say, okay, I know it's a cartoon, there's no physics here, but I want to, I don't want to drag this thing myself. I want to make it do it automatically and see it. And that is done in this toolbar, DMU generic animation. The very first one, see the very first one on the left, it says simulation. You click on it, there's only one mechanism you have, July 1 mechanism, right? You say, okay. And now you're going to get two dialog boxes. One of them, one of them, you drag this thing anywhere you want. Insert. So take this thing anywhere you want. I took it all the way to the end. Insert. Change this thing to 1. Anything, change it from 1 to anything. If you do 1, it jumps from one end to the other end. So let's give it some space to move in and rewind it and play it. There. Now, if you wanted to bounce back and forth like a ping pong ball, okay. Click on this guy. It says, what is the name of this? Change loop mode. So we're going to make this thing go back and forth, ping pong ball. And you sit there and watch it. No physics. It's just a cartoon. Now, remember, you can make this thing slower, or this is slower, or faster with 1, like that. Let's put it back, slower. And if you make the arrows chase each other here, this is going to go from one side. This is ping pong ball, but if you make the arrows chase itself, chase themselves, it just starts from that end, goes in this direction. It doesn't go back. Somebody did not hit the ball from the other side. Good, good. So, if you can't do this stuff, forget about the rest of the problem. I always make the mechanism, check it like that, and now I'm going to go put some physics into it. Not yet, though. Not yet. Now, suppose I want to send my work to a GA, and the GA was too lazy to double click on this thing and then check it like that. Okay, check it like this. Okay. So what you can do, and we're going to ask you to do that, is to create a replay so that the GA does not have to go and do this. Okay. So a replay is, I think it's right here. This simulation that we just created. The second one says compile simulation. You click on it. It says, okay, do you want to generate a replay? The answer is yes. Don't use 1. Don't use 1. Anything but 1. And then say, okay. And just sit there, watch it. And when it's done, a replay has been created. So when you send this thing to our GA to Mark, remember, you have to send the product and all the parts. He or she is going to double click on the replay and say, hey, play it for me. I don't have to do anything. And if he or she wants to make it look like a ping pong ball, just change this looping condition. Now, suppose you said, oh, I like this. I want to put it in my presentation, some PowerPoint presentation for senior project. Okay, so what you do is you go there, compile. This time say, I don't want a replay. I want an animation file. This is the format that it has. That's fine. This is the only format that I know how to use. And I'll just give it a name. First of all, I'll put it in that folder, July 1. Terrible. You stick with July 1. July 1 folder. Where is July 1? Oh, July 6, right? Sorry. Folder July 6. And name of it, I'm going to call my first video. Okay? Say okay. And don't use 1, because 1, all it does is jumps onto the other side. The video is going to be very short. So let's make it 0.02 and say okay. Just wait until this finishes. It's generating that video clip. Your replay is still there. That's fine. The GA can still look at that. And now if you go to that folder, July 6th, right there, I have a video. There we are. You have it, and then you can make it play continuously and things like that. The point is that you can create a video of your animation by creating a compile it and asking for a video clip. So let me close that, go back to the stuff. You're not done yet. Okay, good. Now, suppose I want to know this point, what path it takes. I mean, you don't have to be a brain surgeon to say that, or let's say engineer. You don't have to be an engineer to say that this point moves on a line, okay? You know that. But I want to get it because in some cases, in complicated mechanism, I have no clue what the point is going to move in what path, okay? For example, if you have a single cylinder engine, let me show you. This is going to be your homework for next week. It's not posted yet, too early. You haven't done anything yet. It's just the beginning of this stuff for you, but I want to show you what it is, so that on Thursday when you get it, at least you have an idea. And by the way, from this point on, all sections will get the same homework. Oops, not this one. Sorry. It's not your homework. I didn't need your homework. Just a second. Well, actually, yeah, that'll do it. Okay. That'll do it. Let me go back. Okay. So we have a mechanism like that, and this is going to move, turn continuously. I want to know what is the path of point B. Who knows? You know, path of point B. Actually, path of point B is not a problem. It goes around the circle. But D, what is the path of point D? I have no clue. Maybe something like this. So anyway, generating the trace is what is going to give you that. So let's go back here. This is you don't have to be an engineer to know that this is going to go on a straight line. So you go and click on the trace. See that? Right here, trace, footstep, magnifying glass, like a detective. Trace. Element to trace is this point, for example. And the reference product is just product. That's okay. And say, okay, this is the number of points, that you can ask for it. Okay. Let's see, with a 51. There we are. And if you save this thing, file. Now I have to save the save management. This is the trace that I just created right there. Save as. I'll tell you why I want to do this thing. Let's go to July 6. July 6 folder, trace, put it there. Remember, block on the track. There's the trace part. And why I do this is I can close this and say insert existing component in my product, and it was July 6. Where's July 6? The trace that I saved, I can insert it, and right there. Now, of course, it's not going to be in the video because the video was created before that, but if you look at the replay, there we are. There we are. Okay, good. No physics. This is still cartoons. Now we're going to put the physics in it. I saved it. This toolbar, which is ordinarily at the bottom row, this is one of the utility toolbars. It's called knowledge. And that's the physics that I want to put into it. In CATIA, I cannot give it acceleration directly, but I can give it position. I have to do this math to go from here to here. Okay? So, go back here. F of x. It's a formula. It's a formula. It's f of x. It's a function. Click on it. So what happens? Any information that you inputted in CATIA to generate this very simple model is right here in front of you. It's a long list. All the dimensions that you put, all the constraints, a whole whack of other things, etc. part name, part number, you know, stuff like that. Okay, I'm not interested in these. All I want to do is my mechanism. So notice that all this junk, it's not junk, but all this stuff, when you click on the mechanism, it just turns into two things. It says, as a mechanism, I need two things. Give me the time and give me the position. Remember, this was a 1 degree of freedom system. Give me the position and give me the time. Okay, so we go here, and the relationship between them, of course. So this is the position. Remember, I made it length-driven command. As soon as I do that, this is created. Add a formula. This, add a formula. It says, okay, this position equal to, the equal is here. Don't type the equal in the box. The equal is right there on the right side. You can see that. Now, I want this thing to be time squared. Time squared. Okay. Time. How is time defined in CATIA? It's right here. See that? It's not time. It's not called time. You click on it, it's this weird name. July 1, mechanism / kinematic time. So you can type this over there, or just select it, double click it, and puts it over there for you. And I want this thing to be squared. **2. When I do that, it'll come back with an error message. We'll see. It says, wait a minute, these units don't match. And the person is right. Let's look at it. Double click on this thing again. The left side is dimension in inches. The right side is time squared. They don't match. You've got to make it work. You've got to fix that so that the left side is inches, of course, the right side is inches. And there are many different ways of doing it. One of them is multiply. One of them is take this, multiply by something like 1 inch divided by 1 second *2. Hopefully this will work. I should not get that message there. Because when you think about it, left side is inches, right side, the first thing was second squared, and then I'm multiplying it by 1 inch divided 1 second squared. There are other ways of doing it. For example, 1 inch over second squared can be written like this: inch underscore S2. They'll do the same thing. 1 inch underscore means divided by whatever is easy. This doesn't like it. Maybe. Okay, so obviously, let me put a 1. Let me put a 1. Let's see if that thing works. Good. 1 inch divided by seconds by underscore S2. You have to fix it. I don't care how. Say okay. Notice that we now have physics. If you, in fact, look at the laws, you created a law. There was nothing here before. Now it's there. This formula that you type is right there. If you double click on it, by the way, it'll send you to that thing. We can change it, etc. Now, let's save everything here. We have a law. Now, remember the DMU kinematic, the anchor, magic wand, the joints. You are in charge. You know, you drag that sliding bar. There is simulation with laws. We just create a law. In other words, put some physics into it. You click on it, and it says, okay, I'm going to do it according to your law. According to your law. However, what is your time? What is your time? How long you want your time be? Do I want it to be 10 seconds? I already told you that this block reaches the end at 4.47 seconds. So why should I do it 10? I can do it. There's no problem. but I'm going to go all the way to 4.47. This is the default. 10 is default. 4.47. So I don't want you to do a 10-second. It'll do it for you. It's going to get off the track and, you know, moves on. That's fine. No problem. And I want you to watch this block carefully. I say run. When you run it, this block starts from rest condition, 0 velocity. Initially, it has 0 velocity. The velocity builds up according to the formula 2t, right? Velocity equal to 2t. When t is 0, velocity is 0. When t is, I don't know, 4.47, this is going to be 9 inches per second. So it starts slowly and builds up. Just watch the block. Slowly and then up, builds up speed. Now, just to convince you that it didn't have to be 4.47, I could have used my 10 if you want. Okay, no problem. Simulate it. Goes off the track. No problem. It's back there. After 10 seconds, it reaches. It's still going. No problem. It's over here. Back to 4.47. 4.47. Okay. Rewind. 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 There is physics here. This is not a cartoon. Okay. Rewind. Now, how do I know the physics is right? The only way for me to know the physics is right if I plotted these. In other words, if I plotted the acceleration, I should get 2. If I plotted the velocity, I should get the linear variation. Plot the position, it should get parabolic. How do I do these things? Okay. In order to do these things, you have to create sensors. In other words, I want you to give me the position of that corner point, for example, or that corner point. I want you to give me or plot for me the velocity of that corner point or the acceleration of that corner. First, you have to say, what is it? What corner point? What location? Okay, and that is done in ball rolling down a ramp. The speed and acceleration. It doesn't say sensor, but it is sensor. See, speed acceleration sensor right there. Ball rolling down a hill. Click on it. It says OK. First of all, you can call it a name. I'll say, how about calling top right corner? How about that? Top right. This is a simple problem, but if you have many of these, then you give a meaningful name. What is the reference product? The reference product is the track. You're doing all these things with respect to a stationary object, which is our track. And what is the point? This point, top right corner. I said this. Okay, for example. And we say OK. So sensors have been created right here. See that? Speed acceleration sensor has been created. Now, again, I go simulation with laws. This is where I need to activate sensor. In other words, saying, what is it that I want you to plot? Okay, X vertex. Because remember, this goes down the x-axis. So Y and Z of it is going to be always a constant. So I want the X position. See, they all say no, but when you select it, this turns into yes. See that? When I select this, it becomes a yes. Okay. Do I want the velocity, speed, X linear speed? Yes. Because the Y and Z linear speed are 0. You know that. Think about it. And acceleration, X linear acceleration. Don't close this. Just move it. Oops. Just move it out of the way. Don't close it. And play it. When it reaches the end, means it has done all the calculation. And then I'm going to go and graph it. I'm going to graph the position, acceleration, and velocity as a function of time. Okay, done. So move this thing up. That's why I said don't close it, and say graphics. Okay, let me zoom out. So you get 3 curves. The top one, the red one, it says linear acceleration, x linear acceleration. Hey, look, it was 2 right there. It was a constant acceleration problem. It's 2. The green one is the speed. Hey, look, linear variation. Remember, it was 2 times t. And when t is 4.47, you get almost 9 right there, almost 9. The bottom one is the position. Parabola, remember it was t squared. When t is 4.47, you're going to get almost 20. Right there, you reach the end. Now, on the final exam and on the homework, we're going to ask you to create, for example, a graph like this, okay, and give it to us. Now, you cannot save this. And in fact, when you leave CATIA, this is going to be lost. So what you need to do is a screen capture of that. Okay, put it in a Word file, call it linear velocity acceleration, velocity acceleration position plots. And just like you were submitting PDFs, remember before, put it in a Word file or put it in a PDF file, save it as a PDF file, and dump it in the folder with your parts and products, just like you did with your PDF. Okay. Now let me see your homework problem. There's more to do. We're not done yet, but I want to show you this next homework that you're going to get on Thursday. You're all going to get the same homework. It's all labeled as different labs, but that's because these times I didn't want to change. Okay. Now here's the mechanism. This thing turns. This thing turns at a constant speed. And what you want to know is a bunch of things. It says create the assembly. Of course, just making a bunch of rods is going to get you, and put the constraints. Make the constraints. We're not going to give you 2 marks for making a bar like that. Make the constraints. The GAs are going to check your constraints. Model the mechanism in CATIA over a 2-second interval. Okay, 3 points. So you put the physics into the problem. Oh, it's okay, this is turning at some RPM. The RPM is given, 60 RPM, okay? And then create a plot of the velocity of the point D as a function of time, as a function of time. Displacement as a function of time, 2 points. Now plot velocity versus acceleration, not versus time, versus acceleration, 2 points. And something else. So I think trace give you 1 point, okay? Remember, if you don't go the first step, unfortunately, you lose all of these. Okay? How can you do these if you can't even make it, if you can't even animate it? All right. Now, let's go back. Okay, good. So remember, screen capture this, save it as a Word document. That's fine, Word document, and send it to a GA, just like you did the PDF. Also, PDF is going to work. It's up to you. Now, close this. Okay. Now, suppose I want to plot position versus not time, but versus speed. Okay, so what we're going to do is the following. We're going to go to options. Well, first of all, let's return this thing back to where it was. Return it back. And make sure you clear your history. There's a history tab, clear it. Okay? All right. Now, these things are still selected. So we say options. It says, what kind of a graph do you want? Do you want versus time? The answer is no. I don't want it versus time. I want position versus velocity. Customize. Add. Okay, so it says what versus what. Okay, for example, if position is on the vertical axis, go select it. X vertex, vertical axis. And if velocity is on the horizontal axis, select it. X linear speed. You say OK. You say close. Now we have to simulate. Now I don't know whether we have to simulate or not. Let's check. Let's check for a second. I'm not 100% sure. Let's see. No. Okay. So you have to simulate it. You have to make it run. because the other one said stack empty. If I had not cleared it, probably would have been okay. If I had not, maybe, I don't know. You have 5 weeks to find out. And then graphics. This is wrong. What did I have to go and find out what I did wrong? This is definitely curve 1. This is definitely wrong. Okay, wrong, wrong, wrong. Okay, no problem. Let's do another one. Rewind, rewind. Let's do that. Okay. Option. Customize, add. I can delete the first one, but that's okay. Let's make sure we get this correctly. So I want position x vertex versus speed, x linear speed, right there. And we say okay. That first one I can remove because it's garbage. Close. This stuff is there. I don't want it. I would prefer to clear it. Okay. Run it. Position versus speed. Yeah. Okay, and then when it reaches the end, graph it. Ooh, what am I doing here? X acceleration.
But I think you chose the acceleration instead of the speed.
Really? Why didn't you tell me earlier? Okay, so rewind this. Rewind this. Clear the history. Clear the history. Options. Now watch what I'm doing. Okay, let's delete this. Delete this. Okay, add. Okay, position. Help me. This was this, right? Top right. Vertex. For this axis, I want linear speed, x linear speed, correct?
Yeah.
Okay, and we say okay, and we close that, and we simulate it. Versus time is very easy, you saw that. It's one thing versus something else that is so very often of interest that you have to customize your graph. Okay, reach the end, reach the end. Graph. There we are. Thank you. Okay. Remember, velocity was t, 2t. This was t squared. So it's a parabola right there. We can see that. All right, folks, listen. This stuff is not easy. And don't just wait for 2 weeks because you're bogged down with other tests and things like that. At least half an hour every day will do it, okay? Even 15 minutes every day. But if you wait until next week and then try to do that, it's going to be tough. So we're going to go to our second problem this afternoon, which is the chapter after that, no, chapter 3. Now, I'm going to stop the recording of this and post it on YouTube. Okay, obviously you have it on Blackboard too.